Okay, I'm going to talk in English because I was thinking in my topics before in English, and let's continue with the same dynamic of the past conferences. As Lucia present me, I'm from Universidad de Afid and Universidad to Delft, and today this is the title of my presentation is Lotus Euros Parameter Estimation through 4D Ensemble Variational Data Simulation using Tropomi Observation. First of all, I want to apologize my colleagues for I was not present in the last seminars of your presentation because I teach some course in this time, but please apologize me. Today I'm going to talk about this order of ideas, just a brief aspects of the last seminars to understand where I am standing in this moment. I'm going to talk about the implementation of these techniques in the highly dimensional model that most of you already know, making some aspects understandable now of the 4D envar formulation. Then the Lotus Euros configuration I made for this implementation, some important aspects about the satellite data, which is the data that I'm using for assimilate, and the considerations for the parameter perturbation model, which is the model I'm used to propagate my noise of the parameters and then to get the uncertainty values to modify in my estimation process. Finally, I'm going to show the current results of the emission parameter experiment, and let's go. You know, and I like to show this graphic. The reality could be represented in many ways. We, the mathematicians, like to use models for represent the different physical variables of different geophysical aspects. And the atmosphere could be represented for partial differential equations, which have consideration and restrictions of different initial conditions and parameters involved. In the other side, we have the measurements, the sensors that comes in different packages. This is an image from a satellite sensor which is called Aura, and this remote observation let us have spatial and temporal information that the places that we need to measure. Both words are inaccurate, and you need a recent methodology that is called data simulation and comes from the weather prediction studies in the 80s, and currently many geophysical science are implementing. With this combination of information from two words, we want to improve the representation of the reality. This is a picture that I like to show and I like to update. This is the contribution of the GRIMAT group in this area of data simulation with the modification of the Bouquet and Ash textbook. You can see the different areas, the assumption of the noise involved in the covariance structures of the model and as well as the observation. Different works of our colleagues, and Viviana is also joined the data simulation team, and this work today is in this area, in the 4D envar methodology. And you remember that in the seminar 2019-02, I showed the methodology in the implementation of the Lorentz model. The Lorentz model is a cyclic model, you can see in this way, and it has a very nonlinear behavior that you can restrict with the forcing parameter. And this model you can also configure the number of states. That's the reason it's very useful. You can put a number of states to try to work with high-dimensional models. Once I perform the data simulation using the 4D environment, this could be understood as a toy model, a small model to test methodology. I showed you the last session how the representation of the model being assimilated, the blue one in this case, is going to be updated in the initial conditions in order to follow the true trajectory in contrast of the background, which was the initialization of the model. Something that you have warm in your mind. The methodology wants to update initial conditions in order to have a new trajectory that performs better with the, in this case, a twin experiment, which consists of synthetic observation, or in another case of observations. Remember that I made different assumptions, changing the spread factor, changing the window size of the simulation, and changing the ensemble number. From this point, I start looking for the new implementation. The new implementation in a highly dimensional model, and it's the things I'm going to show today. Just to remember, I'm working in another perspective of data simulation. I test also this methodology with the Lorentz model. It's like a methodology to start testing these new algorithms, first with the small model, then with the highly dimensional. And in this scenario, you can go in step by step, knowing that your methodology is working and is doing what you want. The Cholesky method in an ensemble smoother is something related in some sense with the variational perspectives, in the sense that you take a window of time. You, in contrast of the ensemble methodology, you are not updating each time you have observation, but you have a window of time in which the observations contribute to the analysis to update an initial condition. This is what this equation tell you. The analysis step has contributions with this term, the addition term, that has different measures, different terms that correspond for each one of the measurements of time. Each of these terms have a matrix that is called the covariance matrix, and this matrix in this methodology with the ideas from Elías Niño from Universidad de AFIT uses a matrix that comes from these assumptions. The assumptions that there are states in some radius of interrelation that have impacts in the state that is being analyzed. So you plan with the deviation term, that is the rest between the observation and the model mapped with the observation operator, you can reconstruct the analysis and having the expression for a covariance matrix that evolve in time per time. You can see here from 0 to k, being k the time in which you are updating. This methodology also was tested with the Lorentz with good results. In this case, you can see the states and the Taylor diagram. Okay, this was my last interventions in this seminar in applied mathematical engineering from AFIT, and today I'm going to show you a next important step using the Lotus Euros. Let's summarize the methodology, the 4D environment methodology. We have a model. This is the representation of a model that propagates states in the time, the previous time to the future time, helping with the nonlinear model operation. And also you can propagate uncertainty values and see how in the dimension that the model propagates from the dimension n to n, the dimension of the model. Remember that these models that I'm going to talk has this n very high. It's a highly dimensional model, so this has important disadvantages and implications computationally. This model has a covariance that has a term that has some assumptions, Gaussian assumptions, and this is important when you are going to propose a data simulation method. Depending on the nature of the distribution of the error of the background and the error of observation, you will have to use particle filters on another methodology. The observation are made using the nonlinear operator, which is in this case H. What makes H? H makes the mapping from the dimension of the states of the model to the observation states. So it's reduced the dimensions because in these cases it's more general that you have less number of observation than states. There is now the cost function. The cost function in this optimization procedure is not more than a metric that you establish between the realities. This reality that I want to talk here is the background. Could be understand the actualization of the initial condition, and this is the distance to the observation and the model. When I make the procedure of this metric, you can see here how the const function has, and as you maybe know, I'm sure, is that the procedure of minimization consists in minimize this const function in order to have the value that is going to make these terms in the functional being the less possible. Courier in 1994 proposed the incremental data simulation. That is a method to make the process of minimization more sure, more confident, in order to be more close to the minimization point without having problems in this convergence. The minimization through incremental method consists in understand the next or the updating of the state as the background plus an increment. If you modify the const function in terms of this incremental perturbation, you have this expression and making some algebra. You can have the expression 6, and the expression 6 is the new functional in terms of the increments. You can see how the increments can be visualized as a mapping to a control space variable. When you make this change, you can understand that we are going to make different small steps in order to update the background. In this graphic, you can see the difference of two methods of minimization, and you have the risk in the 4D bar that if you have not tuned the parameters of the minimization procedure, maybe you are not going into the minimum. You can be trapped in a local minimum, for example. And the opposite in the incremental, you can go in step by step, no matter if the step is small, but you are going to the proper minimization point. What is the trick with the 4D bar? The trick is that basically we don't need a joint model. What is the adjoint model? The adjoint model could be understood as the model that propagates back towards the sensitivity of a forecast model. It's very difficult to get the model adjoint, principally when you have highly dimensional states. If you have a small model, 40, 100 states at most, you can code by yourself the adjoint matrix. But having a 1 million states or more, in this case, we have a 6 million, I'm going to tell you later, it's difficult to code, no matter there are automatic differentiator software nowadays that you can find. But the thing is not only that one. The thing is that these models are being coded by many people during the years, and making the interventions to modify adjoint versions of model, it could be like a pain in the ass because in the technical aspect should be very demanding labor. The thing here is using the ensemble perspective. From other works like the Santiago, you remember that this matrix, the covariance matrix, could be created, could be formed in different ways. From the empirical ways, when you have historical from your model and you can recreate the background, or having a multiple propagation of the model. If you have multiple propagation of the model, you can create what is known as the deviation matrix. It's a matrix that relates the difference between each one of the ensemble members and the mean. Why do you make this? Because you want to absorb the most information you want of each one of the steps of the ensembles and their behavior. Once you generate this matrix, you can apply it and the trick of the 4D bar. Let's use the same deviation concept in the observation space. You can see here that we are recreating this term that in the gradient in this functional is this one. And if you are going to use the gradient based technique in the minimization of the functional, you are not going to use the adjoint of the model. You can use this expression to evaluate from the nonlinear propagation. Notice here that this and this are the nonlinear version of the operator, so you don't linearize in any moment. Is very important because the adjoint model basically is the bottleneck in the development in the variational methods in these big models that we have the representation. Okay, I start the experiment with the creation of the domain of interest. You can see we have two domains nested. One differences in days. So from 1st of February to 4th February, should be understood as the window of assimilation. Of assimilation and or of simulation, and in these days we have a window of assimilation. I have a graphic that let you understand better this one. Different characteristics, the methodology that we use, the boundary condition and the spatial resolutions of them, the kind of emission we are using. This is important, the Edgar emission. Let's see what happened, and let's see that we are going to be focused in the updating of this emission, because it was an emission that was created for another countries, for Colombia, and the recent we have is from 2012. So is very, is not accurate, and it's important to have initial condition from emissions very well from this kind of model and the propagation. The biological inventory, the fire emissions, the land use, orography, and specification of domain. This is also a nice plot to understand that the model is not more than a grid cube of many cells. And look, I am using these cells, and the multiplication is like 1.5 million, and it's just the concentration of one contaminant, pollutant. In this model, the states of the system are concentration values. And you can see here, for example, different levels, in this case 5, but we are working now with a 42 level in altitude model. But you can see here how each one of the concentration correspond to each one of the states. Not going to talk too much about the model, because I think you have the general aspects from the works of my colleagues in the past. Basically, the input of different base maps, different inventories to the machinery. The machinery is the differential equations to produce these very fancy maps, with the point being ejected some chemicals, and the methodology drives the fields that creates the pattern where the pollutant goes and then also deposit. It's very nice, the things that you can do with one kind of model of this. In these models, as I mentioned, the concentration are the states. So remember that in each one of the cells, we are going to calculate a new concentration, and we have this in this state formulation, as many cells we have, as that's the size of our state model, a state model that could be of very high dimension. The emissions that we have are these, for these two components, NO in the left, in the right, NO2. I mentioned you that these emissions come from Edgar inventory. The Edgar inventory has, for different components, the daily, the mean, monthly, etc. amount of components that are being ejected. This graphic are in the same resolutions, in the same magnitudes. So you can see that NO2 correspond that a less value that the NO. NO has more areas in the country that has this kind of emission, and also biogenic emissions related. And the NO2 comes for the urban areas. So this is important, because if we want to start updating emissions, what we want is to identify the areas when we want to update. So this exercise was important to plot what we have and what we want to update. Okay, for updating, we want to determine what we want to estimate. Through a data simulation, we can estimate states and we can estimate parameters. In Lopez et al. 2020, we identified as important source of uncertainty the emission factors are going that that was made for PM25 in the Medellin region. So we are in this case using also the same model of propagation that we have for these parameters, that is an additive noise with a nominal emissions are being affected with the addition of a stochastic process that could be configured in this way with a Gaussian noise of variance and covariance specified in this way. We have different parameters here to interact with the model. In the areas of interest, and in my case will be all Colombia, what I made it was to perturbate this factor in an homogeneous or an inhomogeneous way, meaning that if all the places multiply for a value, or each one of the cells could be also perturbed by in a more realistic case. This graphic let you understand what I'm doing in the next procedures. I take the emissions in a nominal expression. It's like a base map. This is an assumed near from Antioquia. And each member is generated with taking different value of the noise in this case in a distribution. So I generate an ensemble space from all this noise once we put into the model, and the model Lotus simulate with these values. This is an annual experiment, but for this experiment, I want to point something. Let's pay attention in the black process, which is the NO2 concentration column, and this is for two components. I first analyze what happened with you only perturb NO and NO2, these two chemicals that I show you, yes? And this is the perturbation of this initial state, okay? But if I say you that I can perturbate parameters and initial states, the parameters and states have different results, different interactions with the system. And as Constantine and Sandu, for example, claims in 2006 and Santiago in 2020, the parameters input more, how do you get more system noise propagation. So it's the system is not very sensitive to initial condition as well as the parameters. That is an important thing because we decide also to continue working with the parameters, because I start with the initial perturbation, but then I see that with the parameters was better to work because it generates ensemble spread during the process, and this could be interesting for the procedure because, as I mentioned, I'm using the ensemble to obtain information. The more I want, the more ensembles I can propagate, but you have to take in mind that this is a very computational expensive work, so we are limited of the number of ensembles. Well, I reformulate the const function. The const function is being reformulated in terms of the parameters. Look here that I put now the parameters that I'm going to estimate, the parameter of the background, the covariance matrix, the prior covariance matrix in terms of parameters, and now this is the one that I'm going to to estimate. What is important to see and you to understand the dimension of this one. What if I was trying in the first with initial states with 1,000,000 of states generating this matrix. Now I'm reducing drastically because the parameters I'm going to be in some locations. So the dimension of the problem in this case is reduced. For the next experiments, I'm going to show you and use always these three metrics of error, statistical measures of the behavior of the procedure. Each metric has its own advantages and it's very useful to and very common to know to see these three metrics in the data simulation area. Okay, this is also the part of the observations. I have the model. I have the model being propagated and disturbed in the parameters, yes, but I need observations. This is not a nice plot I made that is the heritage of the atmospheric measurements. As you know, there are satellites since that time ago, but the interest of measuring the atmospheric composition just comes from the Nimbus initial missions, and these missions also contribute to the NOAA programs and the weather research programs in the United States, instruments of the different sounding methodologies, the MVSAT and the Siamak in 2002 operational satellite nowadays, the government platforms, and spectrographer in orbit that let us understand the chemistry. And in each one of the evolving instruments, the resolution is being reduced. Nowadays, we have more recent instruments like the Yarce, the Yarce, the CRIS, and the OMIS instrument that is very important for NO2 measurements also. This graphic I want to show you is because the next 10 years are really planned in the atmospheric sensing. We have in the world three big satellites that are already not in orbit, but now they are financed. That is the Tempo, the Sentinel, and the GEMS. Will be the first constellation until 2030 of geostationary measurements for air quality monitoring. And this is very important because the spatial, the temporal resolution will be reduced a lot. Just if we have for our instrument, the Sentinel that I'm going to talk later, the one that I made measurements and the procedure, only one measure per day, they will have in the next decade, one measure per hour. So the valuable information that we will have will be very important. This is a satellite that is very important also because it's like complementary for the Sentinel. I'm going to talk later, and the Chinese version of the Tropomi nowadays. It's important also to claim that in Colombia there's no plan for a geo orbit. So will be very nice that South America in a future have this necessity of measuring in more spatial frequency. This is the product of the Netherlands nowadays, the instrument that can sense NO2 highly resolution, and it's a satellite that has a solar synchronic orbit. So it means that the satellite can go daily for all the globe area, and having a overpass or two overpasses depending of the layer over Colombia around the 1:30 p.m. This is the comparison of the pixel resolution and is very important information. This satellite in the last 6 months, just a curiosity, has been relevant in measurement how the COVID in the impacts in terms of the decrease of the less human activities in all the world from the lockdown, and different regions has drastical changes. For example, in Europe, you can see how the valley of the Po River, the agronomical area of Italy, reduced the pollution of NO2, and also in Colombia in the last months could be viewable. But in March, we remember we have this high fire as a pollution dynamics and bad quality from that. This is a graphic of Colombia, how it looks, and you can see from measurements, if you have in mind the emission spots from the Edgar, now you have from the observation the values of NO2 that we are interested. Other nice images from Tropomi and how could be useful. You can see here in Colombia, in Barranca Bermeja, our biggest refinery, how the patch could be sensed from the instrument, and also this big minery activity is also very, very high in values. You can see here how this minery that is located here has actually the same magnitude levels for this time of period and for others of a city. So the activities that pollute in this sense could be now measured from space. The algorithm procedure of the satellite consists first in 3 steps. The first steps is the retrieval, when the differential absorption spectroscopy method is used from the light. The concentration of all the column is retrieved using lookup tables. There is then a separation of the slant column density that separates the stratosphere values and the troposphere values. And there is a third procedure, multiplication with what is known the air mass factors from different instruments for the same, calculating some column properties. You can retrieve the vertical density. That are the ones that we make in use in the pipeline I'm going to show. Each one of the steps aggregates error. So this error of the observation is the one also that we have to take in account. Once we make the first step, downloading the data that has this procedure, we are using now a methodology from 2020 from TNO, our colleagues, that basically takes this data, crop the data to some region of interest, take the data and remap the data to the grid of comparison, and then make another important step that is called the kernel sensitivity transformation. Is the way that you put information from temperature, atmospheric pressure, many parameters from the atmosphere in the column to have the more real representation. In this GIF, I show in the product final and compare with the Q flag. It's a flag of quality, which you can filter data that you don't have and big confidence, and this data could be related to different aspects, and it's not the concentration we want. I made a first experiment of 15 days of running just the model with different value of quality flags. Here is the comparison between the 0.54 and 0.75, and just taking in account that many of these data has non-values because the filter removes. So if you are going to take mean of the data, take in account to take the mean in account, the non. So because if not, you are going to decrease the overall magnitude. And I start looking for differences between quality flags of the two maps, and then the statisticals. You can see here the mean factorial bias, the correlation factor, the root mean square. This statistical let us know areas where the products from one quality to another have changes. This is also the 0.85. And from this first attempt, the important thing was to understand that there is not too much difference between the 85 and 75. And this also a conclusion that we validate here from Bijan, another student, a postdoc student in TNO, that is searching the best quality flags for filter the data. So for Colombia, it's enough to use the 0.75, this comparison we made. And you can see now that I start changing the areas of estimation and the areas in terms of inhomogeneous and homogeneous perturbations. First, I start with this one, but the results were not very significant. So we start making like an increase of the buffer in order to have more area to interact with the parameters. Let's see, for example, what we made. Nowadays, I have this pipeline. The pipeline is developed in one part in Bash and Fortran scripts that interacts with the Lotus Euros model. That is also important to say, because if this works in the future integration with the model, for example, that is developed in Fortran, would be direct to translate. So we make the observation going to inside the pipeline. We compile and use the folder that generate the perturbation as well in non-homogeneous and homogeneous way, propagate the ensembles using the Lotus Euros, merging and adapt the observation in order to start the 4D envar methodology. The 4D envar methodology consists in the pre-processing of the outputs, and with some parameters of assimilation, the analysis step is performed. Different inner loops, the incremental procedure I told you, and we estimate parameters, and finally some routines of visualization. What I'm doing is this one, just to show the recent results, and I take the first 4 days of February 2019. The first 2 days are what is known like a spin-up of the model. It's very common to have a previous time having all the model just propagating to the future. And once we are here in the 3rd day, we start to assimilate. When we make the process of assimilation, we are going to estimate the conditions. And these conditions is the one that is going to work to forecast the model, and we can start moving all this procedure to another window, and then having in a future operational system a subsequent a sequential procedure of this methodology. In the next pictures, I'm going to show you some of the results that we have. This was the first one. It's not very good in terms of the dimensions I take are very low here, but it's here to focus that the things I'm going to show you. I'm going to show you the free run. Is the model just going without assimilation. The tropomy, that is the data of the satellite, and this is the output of the system for the assimilation. This is, you cannot see very well, but this is the estimation of the procedure just in 1 point. So that's why we start doing in another way, having a big buffer. Look here, 9 grid buffer. Now I have the tropomy, the free run, and the retrieval. Notice here is very important, this is that in this area, when the tropomy, like the satellite said us, guys, the magnitude of the concentration are not too high. You have to make something. So the assimilation understand, because the free run take just information from the model and say, okay, this part is very high. It propose with the estimation of these parameters that the output would be less. So this will the first results that tell us that, okay, that the algorithm is trying to follow the information of the satellite that we put. I start then putting more ensemble members and changing parameters like the row. This is the one that controls the gradient in iteration and the number of iterations, and making the same comparisons, but in this time also with the help of more qualitative way, like the statisticals, to compare the both and show the areas with over and subestimation. And you can see different results, changing parameters here, and basically the last iterations I'm performing consist in increase the grid cells to the areas that the first experiments of the 15 days and the recent ones tell us that we have to update. Here we have the principal cities of Colombia in terms of densities, but also points that we have necessities of updating. Finally, this is the one of the latest results, when you can see that this big number of ensembles and iteration, the retrieval could be corrected at least to follow the magnitudes of the satellite in some areas. There are areas, for example, that also improves or not too much, but it's the fact there are a lot of variables that we have to continue tuning and improving to have the best of the process. Okay, just to finally, I'm going. This is a very computational, expensive method. In each one of the rooms, I take some days in our labs computers, 8 cores working, but I'm doing the same methodology with Apollo. Having some drawbacks because the model, as you know, is a compiled model. So you have to compile each one of the changes are made in Apollo. So, and you compile in Apollo, if you know, in the local your environment, but you cannot compile in the run. So I have to split the parts in a compilation scenario and the other part in the run scenario. So it was some of the new procedures in order to, the idea is to start moving to a very high number of ensembles and different drastic changes and different iterations. The preliminary conclusions I have is that this method in this moment estimate different configurations for emission parameters in Colombia, incorporating satellite information with its own methodology that's validated in terms of quality flags and different window time domains. The pipeline procedure in technical aspect is working, and nowadays current work is more validation to validate hypotheses very recent of estimation parameters, for example, TAMO 2020, in which the methodology is driving the plume in scenarios. This is very important also, and make me us think how to incorporate another kind of information to my estimation procedure. Thanks for let me present my work, and this is a nice picture of Julien Chimot, a thesis from 2018 of TU Delft. This make us to think that also all this data should work for the decision makers. We have a lot of measurements, model information, but anything will happen if the people that take decisions will have accurate decision. Thank you very much, and I finish with this nice picture of the two beautiful campus I belong.
Thank you very much, Andres. I appreciate so much your presentation and your responsibility with this seminar. I really would love to know if some of you have questions and or something to say about the Andres Yarce's work.
Hola, buenos días. ¿Me escuchan?
Sí, señor.
Hola, Andrés, ¿cómo estás?
Muy bien, gracias. ¿Cómo has estado?